Sorry. Yeah. Recording. Yeah. Okay. So welcome again, everybody. Thanks for attending this seminar from the Master in Robotics, Graphics, and Computer Vision. We just for Tali, we not only have students from the master, but also researchers from different research groups from the department attending usually. So we have the pleasure today to welcome Tali Treibitz, that is a dear colleague and more than that, a friend. So I'm really happy that she managed to make a little slot to give us this seminar. And I hope you all enjoyed this very interesting talk. Tali got her PhD in Technion from Israel. Then she was working for a while at UCSD in US, where we were collaborating together. And then she was back to the professor position at Haifa University, where she is leading the lab. And she was also founder of a very interesting startup. I don't know if you guys had the time to check out the profile of her. But yeah, so maybe let's skip long introductions because we are a little bit short with time today. So let's start with the talk. The floor is yours, Tali. Thanks a lot again for accepting the invitation.
My pleasure, and thanks for the invite. The plan was to visit in person, and it will happen. I know
Yeah.
it's recorded. It's recorded. I'll come to visit.
Okay.
Okay. So as Anna said, I'm leading the Vision Marine Imaging Lab at the Department of Marine Technologies in the University of Haifa. We belong to the School of Marine Sciences. That is an interdisciplinary school. It has only graduate studies. We don't have undergrads. And as I said, I belong to the Department of Marine Technologies. We also have a marine biology department and the marine geosciences department. So this makes it interesting and interesting projects. So in my lab, we work on I usually divide it to three different topics. First, we work on underwater computer vision algorithms. We also develop novel underwater imaging systems. In our center of the Marine Technologies Lab, we have a nice workshop, 3D printing, soldering, and so on, a pressure chamber, and we do a lot of hardware ourselves. We also have a test pool and so on, so we are very equipped for also working on hardware testing, going out to sea and so on. And we also work on vision for marine autonomous vehicles. So I understood from Anna today that the crowd is mixed. I decided to mention a few projects and go into one of them in detail to hope, that everybody finds something interesting, and maybe it will lead to further discussions later on. First, I wanted to show you, I did this recording from Google Maps. So we are on two different sides of the Mediterranean. Your guys are on the west side. We are on the east side. I wanted to show you where we are located and also to invite you to visit our facility. So if you look at Israel, I'm located in Haifa, which is in the north part of the Mediterranean, as you can see here in the movie. So we're really, the center and then the lab is located really on the beach. So I wanted, yeah. So if you zoom in, you can look at the street view and yeah, see the building, so the parking, and then this is the part of the beach, and this is the building we are located at. So the building belongs to the Israeli Oceanographic and Research Center. So this is a governmental agency, and the university has some lab space here. So you're seeing here different views of the institute. So hopefully this gives you, make you visit us. So, and there was another reason I wanted to show it to you, not only to, make you visit us, but also to show you actually we're pretty used to having all these, having the ability of going to Google Maps, as I did when I did this movie, look for a place, see how it looks like, and this is something we got used to this. But if you look at the entire map, you see that we have this ability for the land areas, the inhabited areas, but the sea is very, it's kind of empty in the map, although the sea is not really empty. And if you look at the Google Earth view, you can see a little bit of more detail. In the sea, you can see a little bit of the topography. So the dark blue is deeper areas, the lighter is shallower, so you can see a little bit more, but that's all. You cannot zoom in and see, where there we have corals, where do we have fauna, and so on. We are missing this information. It's not that Google is missing the information, the entire humanity doesn't have good information about that. And this is like the overall message I wanted to talk about. So ideally, like we have Google Earth, right? We want to have Google Ocean. So to have high resolution 3D photographic data for the entire ocean. These, what you see here are 3D models of coral reefs. My PhD student, Matan Yuval, is taken mostly in the Red Sea, in the Israeli Red Sea in Eilat, but also in some other areas in the Caribbean and so on. And so we have some models, but this is really, if you look at the size of the ocean, this is a lot of work that went into mapping very small areas. So the question is, and by the way, I know there are graphics people here. So Matani keeps collecting data, and we have all these 3D models on Sketchfab on our lab page. Now we have over 140 models. So I know it can be interesting to graphics people. So I invite you to look at the models and maybe suggest collaborations about them. So when we think about mapping the ocean photographically, we're still far from it, although we have very advanced capabilities of mapping on land, right above water. So what's missing for that? There are several things. First, the ability to do autonomous data collection. There are autonomous vehicles, but I'll talk a little bit about their current limitations. There are also issues when we're looking at photographic data on visibility and color, automatic analysis, and also scalability. The ocean is huge, and how do we achieve more data? So these are topics we have projects around, like we also have additional projects, but this challenge kind of sums up the vision of the lab, where we want to advance all these capabilities in the ocean. And as I said, I wanted to talk about a few related projects. So, and I'll start with the visibility and color. I understand Daria already gave a talk in this forum, so I won't give a talk about this method, and I'm happy you got to hear Daria. She's an excellent speaker. So we developed together a method for color reconstruction of underwater models. This is just a glimpse of, I don't know if some people here didn't attend Daria's talk. I won't talk about this method. But we have a lot of activity in this area of visibility and improving the appearance of underwater scenes and recovering visibility. What I wanted, and I don't know if Daria showed that when you take the 3D models and do the color reconstruction, so this is the same model, but on the left one, this is the one with the color correction. So then using the color correction, we have more accurate information on the corals, the biologists can use it better, and so on. So as Anna mentioned, we opened a company, Sierra, that aims to enable to commercialize our capabilities in visibility enhancement and in general on underwater computer vision. The blue economy is, I learned only last week that it's the largest sector, largest growing sector currently. So largest growing, it means now it's small. So something that is small, it can grow fast, but it's growing fast because more and more activity is going into the ocean. In Israel, for example, more than 50% of the drinking water are actually water that come from the sea, that are desalinated from the sea, and so on. So here you see it's not the method we developed with Daria. Here we develop kind of a different method that can work in real time. You see on the left the original videos, and on the right our videos. And now we have in the company, we have a software that can, basically this is a software solution. So we can connect to any underwater camera in streaming, or also open files that are saved, and do the visibility improvement, where our emphasis is to expose objects that are not seen in the scene. So not necessarily do accurate color, but more for commercial use, inspections, and so on. Expose what, like, see as far as we can see, so people can actually work in sea, can actually do reliable operations on sea. And what's nice here that it can work on both ambient and artificial illumination. And as I said, and the method doesn't need any prior knowledge. So we don't need to know the depth or the water type and so on. We estimate parameters from the images and do the correction. And, oh, sorry. This is, we have a pretty simple software now. We're now improving its appearance, but we started selling it to some pilot customers. And we also have a camera with an embedded version. Hopefully will be operational soon, a prototype where the camera itself has the real-time correction. Okay, and this is still work in progress, but here we try to do segmentation of fish. This is a difficult scene. I mean, look at, there are tens of fish swimming there, but basically what we saw that when using on the right, it's our enhanced video, it's easier. I don't know why this one stopped. The segmentation, it's easier for the segmentation to find the fish. It's still a difficult problem, which we're still working on. Okay, and all this, what I showed you is visibility on single images. First, I didn't say, if you have questions, feel free to interrupt, okay? Anyway, it's difficult to give a talk online because I don't see you and so on. So if you have anything to say or questions or comments, please feel free. Okay, and I wanted to concentrate in this talk on a new paper we have accepted to the coming CVPR, where we look at a slightly different problem. So, and what to do with the noisy images. So if you look at this underwater image, so, okay, this is an underwater image of a structure in Elat. We did the visibility enhancement that we have in the software. We get, oh, sorry. No, sorry, something is messed up with the animation. Okay, sorry. So we do the illumination adjustment, but there's still noise in the images, and we wanted because the medium itself is noisy, and we asked ourselves how to remove the noise. So we wanted to look at burst denoising, and actually our method, now you will see. You'll see examples that are not underwater because we realized it's a broader problem. So just to, okay, I'll show you the result. Just to recap, so in burst denoising, we look at using several images for denoising. So obviously, when you have several images of the same scene, the denoising is better and more powerful than doing denoising on a single image. So in theory, if you have n noisy samples, you can reduce the noise by a square of n by if you average the images. So if you look at the SNR, you can increase it by the square of n. So this is a known fact. And this relies on having, a tripod. So if you look at this scene, this is synthetic noise. If we take the same image and just add different level of noise, then we can even do simple pixel-wise averaging if nothing moved in the scene and get a much cleaner image. The problem is when you're diving and want to do that, you're diving without a tripod, then things are moving. We will never have aligned images. And then the question is what to do with that. So in burst denoising, when you're moving, then if you just do averaging, of course, you have motion blur and the scene is blurred. So the goal, the main challenge in burst denoising is actually overcoming the misalignment more than the denoising itself. So, and when you do burst denoising, you combine both the temporal denoising, so using information from different images, but also the spatial denoising, using information from different parts of the image. So previous methods assumed a pretty small motion between the images. So I'll show here three recent related works. So this work assumed a kernel. So in this work, they trained the network to predict kernels that will combine the information for each pixel, determine how much information to take from the pixels surrounding it temporally and spatially. But they did a kernel of 5 by 5. So this is a very small kernel. The issue is that you predict this kernel per pixel. So once you start increasing the kernels, you need a lot more memory and a lot more compute time. So it's difficult to do it. The follow-up work, BPM, they managed to use larger kernels by assuming they are a linear. The kernels have a basis, so they're predicting the coefficients of the kernels and not the kernels themselves, but still they did 15 by 15. So assuming this is the maximum movement between the images. And there is another related work that actually the network, what they trained the network to do a map estimation, and they assume they're doing, before this network, they're doing a pre-alignment with optical flow. So we wanted to tackle this problem from a different view. And we were inspired by research image synthesis methods like NERF. So I'm assuming most of you heard about that. I'll just do a small recap. So what happens in image synthesis, we have an unknown target view. And we assume you have other views of the same scene from different poses. And we want to use them to predict how the target view looks like. So we want to synthesize the target view. Now, when we look at burst denoising with movement between the cameras, our insight that it can be formulated similarly to image synthesis. So we also have cameras from different views. The difference is that now the target view is not unknown, we have it, but just it's very noisy. So the insight was that we can use the other views to denoise it using tools for image synthesis. So as I said, this is based on NERF, so just a small recap. In what NERF are doing, they're using tens or hundreds of views of the same scene, and they train mostly overfit some MLPs to the scene, and then they can generate an overview. The way they look at generating an overview, when you have the target view and you have a pixel, let's say you want to know what is the color of this pixel, you send a ray because everything is calibrated, right? So you can project the ray that this pixel images, and then you don't know where the object is, right? What is the distance of the object from the camera? But then for this, use the other view. So let's assume the object is here. It means if the object is here, this 3D point in the world is projected to the other views in these pixels. So then we can accumulate the color of these pixels in this projection and see that here we guessed the distance of the object correctly. So actually the accumulated pixels, they have very similar colors. It means that probably there is something there, right? Because the reprojections kind of hit the same color of the object. But if we guessed that the object is here, it's not on the trunk, right? It's like just closer from the tree. Then the reprojection in each view, it will hit a different color of the pixel because this is not, this assumption is not true. So if we accumulate the colors of the pixels that adhere to this distance, then we get a variety of pixels that don't agree. Okay, so what NERF does is for every distance on the ray, it can generate such a vector and see which one makes the more sense. I simplified it a lot here, so don't, but basically, if we got a high density of pixels that agree, we can take the color from them. And this is a lower density, and the color, we cannot infer the color from this one. So in the context of burst denoising, the NERF setting is not applicable because the NERF trains per scene. So what happens there, you give it tens or hundreds of views of the same scene, and the network learns just this single scene, and the training time takes around a day. And then once you train the network to learn the specific scene, you can produce novel views. We wanted to look at a different architecture that's called the IBRNet. What they did is the idea was to take a small number of views and pre-train a network. So the train network, it doesn't train per specific scene. It learns, given a collection of images, how to predict the correct view from them. So I won't go over all the details of the architecture. I wanted to give an overview and explain what we did with that. Okay, so hopefully it's not too, the overview is not too short, but ask me if something is not understood. So what happens there in the network, there is a pre-processing of extracting features and so on. And then in the training, each pixel, as I said, we can gather for each target pixel, we can gather a vector of all the projected pixels, as I explained before, and their colors. We can aggregate, they are aggregated, and they're going into some machinery consisting of MLPs and so on, to eventually predict the color of the pixel. So in training, this is done using the ground truth, and then in inference, the network is supposed to output the color of each pixel. So what we marked here are a few. This is done per pixel, and this assumes ideal images that are not noisy. We added a few components to this network to make the network aware that we think there is a high noise in the scene, and then enable it to cope with the noise. I won't go over everything. I wanted to talk about this part because I think it's the most interesting, and it gave some nice insights. So there is a part that's called feature aggregation or view aggregation, which, as I said, takes all the per pixel, all these vectors, and decides eventually what is the real color of the pixel, of this target pixel. So, um, okay, but when you look at it, so when, as I said, if it's a high density pixel, it means we aggregated the same colors from all the pixels. This says that there is low variance in the surrounding colors. And if it's a pixel, if we guessed wrong the distance, there is low distance and there is high variance. This is without noise. But what happens when there is high noise in the scene? Also here in this case, where we guessed correctly the distance, we can receive high variance that stems from the noise and not because we projected different, like the wrong pixels on the pixel. So the question was how to distinguish between this case of high variance because the projection was wrong and we didn't predict the distance correctly, and high variance of the noise. So we added what happens in the network. Basically, the only thing connecting between the views that was in the original network was the mean of the features and the variance. So this was mostly the input that the network decided on it. So if I simplify, of course, there was learning involved. That simply you could say, okay, if the variance is low, take the mean, this is the output color, right? If the variance is high, ignore that. But we want, as I said, now in the case of noise, it's not so simple. We added here a transformer that the idea was to connect between the views. So have the network also really look at the differences between the features in the different views, not just on their statistics, but on the actual features, and try to understand, are the differences between them, are there because of noise or because we fell on different pixels? So we changed that, and I'll show you the effect of it. So this is what we did is we zeroized some components just to see the importance of how things affect the network. So we did an experiment where we zeroized the features that come from the pixels and only fed the network only the mean and the variance. And this is the result of the original network, which shows you what I said, that the features are going in there, but the network ignores them. It takes only the mean and the variance. If you use only the features and don't give the network the mean and the variance, you get the picture, the result you get is blurred. It's not a good result. We expected, right, an overview sharp result. And once we added, so this is an experiment we did. We took the original network and trained it on noisy images, so without our additions. And you see that already when you train it with noise, it gives more importance to the features over the statistics. And if you zeroize the features, then the result is not sharp. And as I said, with our addition, so you see that the features, just using the features gives you almost a really good, like the perfect result. Whereas just using the mean of variance, it's also a blurry result. So this shows that what we entered, we gave the network the ability to really look at, compare the views themselves. And as I said, we had a few other changes to the architecture, which I'm skipping because of time. I wanted to show some results and also discuss them. So we took this is a data set of scenes from different views. It's called the LLFF. It was published in previous NERF's works. So what we did, we added the simulated noise to it. So this is the ground truth clear image. This is a noisy image with a pretty large noise. The reason that we worked with such noise levels because this is common underwater. The visibility is bad, the water attenuates the light, and therefore images are very noisy. And this is our result, where look at we marked here with squares delicate areas that were reconstructed. Look at the noisy ones and our reconstruction compared to, this is a comparison to DPREP, one of the papers I mentioned that in our experience had the best result. So when you look at it, the result looks nice, right? It gives you like it does denoising and a smoother result. But if you look at this area, there are artifacts that stem from, for example, here you see that we missed the stem of the flower. And also here, there are some motion artifacts that don't exist in our method. You see here in the orange square, we reconstructed fine details better than the previous method, the previous state-of-the-art method. And this is because this method and also the others, they don't handle the motion explicitly. Here we use the geometry of the scene as an implicit prior, and it enables better alignment and denoising when we have large motion. So, and this is another previous BP. Okay, this is another scene where we also marked interesting areas. So this is the ground truth, the noisy images. Here it's interesting because there is some text written on the whiteboard. Under the noise, it's very difficult to, I mean, you cannot see the text. In our result, you cannot read it. So we didn't really reconstruct the entire text, but at least you see that there is something written here. Whereas the other leading method, it's completely washed away. You see, like it lost the details of the text. And also here, there are artifacts in the reconstruction of some objects. So overall, when you look at it, the scene is denoised. I mean, it looks nice, but when you look at the details that are missed, so this is the previous method, it has some artifacts on the chairs and so on, because it's difficult for it to cope with the larger motion. And okay, and we have some real world results. So this is a dark scene, and I think it's my student's apartment. So when you try to equalize just the light, so you get this. So this is just, you know, normalizing the scene and trying to get out the details. It's noisy. And then this is the average, and this is our result, where you see that a lot of noises, we reduced a lot of the noise, but also managed to keep fine details like this gap in the floor, this line, and details of the flowers. Whereas this is the previous method, things are more blurry, like it is the noise, but things are more blurry, more fine details are missing because of the difficulty to align them well. So again, this is ours, and this is the previous result. We have more, okay, I'll show the numerical evaluation. We have everything on the website, all the like additional results, and of course the paper itself. So what's interesting in the numerical evaluation we did it as a function in the simulated data. We did it as a function of noise level. The numbers you see here are gain levels. This was defined in previous works, but you see here below that the corresponding standard deviation of the noise. So, and we did the evaluation for all the noise levels. So of course, all the methods, when you have higher noise, perform not as, I mean, the performance deteriorates. Our PSNR, this is the blue, is higher in all noise level except of one, which is actually no noise, more or less. And what's interesting is that when you look at the two previous methods, their performance kind of changes. So lower noise levels, you have BPN works better, and then DPREP kind of takes over. And what's interesting is that PSNR, you know, it's a pixel-wise error measure. SSIM and LPIPs are more like a visual, more visual error measures. And then they're actually DPREP performed better. Probably, maybe it's because it's more visually pleasing, but as I showed you, it has many areas where with artifacts or things that are not reconstructed well. So I'll skip that. There is an ablation study, of course, in the paper. And just to summarize that, everything is detailed on the website. We took an image synthesis network and added the components to make it noise aware, and we showed that it achieves a state-of-the-art result in the inverse denoising under large movement compared to two very recent works. And hopefully you'll have some comments or questions, but you're probably going to say this is a long runtime relatively to other methods, and you're right. But there are actually in the past 2 years, the nerf field is exploding, and there are many new methods that have faster runtimes. So hopefully we can leverage that to also reduce the runtime, and yeah, and use that in more difficult underwater scenes. So I wanted to show a few more things on our vehicles, but on if you have questions on this paper, this is a good time. And I'll drink some water. Okay, so think about the questions. And I know there are some robotics people here and so on, so I wanted to show you some of our autonomous vehicles. This is a newer activity, and we're now in the processes of learning to work with them, gather data, and so on. And also finished integrating some sensors. So we have two vehicles in the lab. This is a Spanish vehicle from from Girona that was developed in Girona, and we bought it from them. So we bought this is an autonomous underwater vehicle capable of hovering. We actually added this area, the yellow area, that's the payload area for the sensors. We added downward looking cameras, so a stereo pair, artificial strobes. And also we have colleagues that are mechanical engineers. They worked on stabilizing the vehicle adding these side thrusters. So it's the Spanish vehicle, but with some development and changes. So this is how it looks like underwater. Maybe it's hovering. I'll start with showing you the deployment. So this is here with a small boat deploying the vehicle. I don't know if the noise of the water you want to leave it or it gives a nice atmosphere. And so yeah, the vehicle is descending, and you can see it nicely gliding in the water. What we learned working with this vehicle is that it's not easy to work with autonomous vehicles underwater. As I said, our progress I admit, was slower than we thought. We had so many plans for this and realized that reality makes us progress slowly. Here it has a GoPro. This was before we added the cameras. So you see, for example, the deployment from the boat, you need a sea that is kind of quiet and so on. So the experiments are very dependent on sea levels and other factors that also make it difficult to plan. But I'll stop complaining and show you some results. So we managed to do some mappings. These are a mosaic we did with the downward looking set. So, and also the 3D reconstruction. If you look here, there is a stingray. So we aimed at pretty high resolution, and with the stereo pair, it's a nice, it's a nice demo to show that there was this stingray that got scared from the vehicle that came above it, but we have from the stereo we have the 3D of the movement, so it's kind of nice. You see the wings flapping, and you can do the 3D. So yeah, this is not a lot of great news for vision people. Of course, you can do it, but it was nice to do it really with an autonomous vehicle underwater, and our biologist collaborators like it. And we also captured the turtle outside the lab here, so there is some life and it's nice. But then we realized there is the difficulty to deploy it to do large areas and actually interesting areas, that the obstacle avoidance capability is very limited. So usually underwater, you do obstacle avoidance acoustically, not with the vision. Because the vision is limited, it's difficult to see. So people usually use acoustics, either pingers or more like sonars, to do the obstacle avoidance. But then this is limited because the sonar, the acoustic signal is not so, the resolution is not so high, first, and second, it doesn't have the vertical axis. So it gives you, I'll show it soon, kind of a top level view of what's ahead of you, but the resolution is, you have it on the x-axis, you don't have it on the y-axis. So if you are if you want to navigate in coral reefs environment like I showed you before, and you want to get close to the coral reefs to get, I see there are questions, so a minute I'll answer them in the chat. If you want to get close to get good images, the sonar is not reliable, so you can't send a vehicle with the current obstacle avoidance to image 3D, the complicated 3D structure and so on, because when you're using, when people use sonar for obstacle avoidance, the instruction is, if you see something ahead of you, just go above it and, just pass it, go high up until you don't, it's not in front of you, and then pass. But this is not suitable if you want to really swim around corals and so on. So we realized we need a forward-looking camera. We integrated that into the vehicle, and also a forward-looking sonar. In the meanwhile, we also, actually in the slide it's larger, but this one is actually much smaller than this one. So this is an ROV. It's not an autonomous vehicle. It's controlled, it's connected to a laptop with a tether, and so you operate it from the boat. But so this is not an autonomous vehicle, but a good platform for us to gather data and play with it. So we purchased that. We upgraded the camera, and now actually last week we also added a sonar here. So, and we have a project actually also with the European project, also with the group from Girona and from Germany, to look at this, do obstacle avoidance in complicated areas. And these are pictures from experiments we did in the Red Sea in Eilat, where this here, now this is an autonomous vehicle, but you see it has a tether. So we connected it to a buoy on the surface with a tether, so we can control it to go close to the obstacles, because otherwise it doesn't know to avoid them. So here it is controlled by a remote control from the surface, so we can put it close to complicated areas like you see wrecks or this is a man-made structure, to gather data that we can develop. So this is really, I don't have any results to show. This is a work in progress. And what we are also trying to do here is to understand how to combine the information. This is by the way, the forward-looking sonar information. And this is the forward-looking camera information. Here it's just a simple rocky reef. So you see it's difficult in both images, it's difficult to understand what's going on. So we're trying to develop a method that will at least tell us, okay, this point is this point here. Now you have more information trying to understand the scene. So this is work in progress, just mentioning that in case anyone is interested. And actually, yeah, this is this is what I planned to show. So it's a good time to stop. Okay, so wait, I'll open.
Yeah, we can go to the questions. And
Yeah,
thanks, Tali,
so
for the talk. Really interesting, really
uh,
compact. A lot of things.
what?
A lot of things in 40 minutes.
Yeah,
Very
so I hope it wasn't too packed, but I knew
no, no, really nice.
the
I
audience
think
is
really nice.
diverged, so I wanted to mention a few things.
There are a couple questions in the chat
Yeah, I
from
opened it.
Juan.
There was a question about the transformers. Okay, two good questions. We didn't try. I don't know if the question is other transformers or something completely different. We found that, so the question is we didn't try it. Other things, what we put there worked. It is beneficial because we saw that it really combines the information from the different views, like kind of compares them, or a mechanism to compare between the features of this pixel from the different views, and not only look at the statistics. I agree that there are probably other ways, maybe probably better. There is always a better way to do it, but we saw here that uh, it it improved I mean, it gave us the result we wanted. And the second question in the chat was how much different is the noise underwater in comparison to traditional scenarios. This is a great question, mainly because what happens is that the noise is not different, the SNR is different, because what happens is the noise is camera noise. You have you have signal independent noise and signal dependent noise. It's the same noise, but the scene is different. So what happens underwater, you have the part of a lot of signal comes from scattering. So then, and the scattering is signal in the camera, but it's not a signal from the object. So the SNR is actually much lower because the object itself is captures a small part from the signal that comes to the camera. So it's true that, and this is why I mainly show the results that are above water, because underwater we also have nice results, but they're not as nice, probably because we need to adjust more with the noise model and so on. I don't know if it answered the question.
Yes.
Okay. Yes.
So we have another hand raise. Nestor, please go ahead and ask if you want.
Yeah. So I also have a question about the denoising method. So all of these nerve-based methods, they don't need any kind of geometry optimization for the scenes, if I understood correctly.
They don't do geometry optimization, but they do need the poses between the cameras. So maybe I'll quickly scroll back. So the thing is, yeah, they don't reconstruct. If the question was, do they need the 3D structure of the scene? That was the question.
Yeah, kind of like, because like the original nerves did the geometry, like they modeled the geometry implicitly, so they don't need to do that anymore for these methods.
No, so we also the nerve doesn't assume they know the 3D, and we also don't assume we know the 3D. From you can output a depth map from nerve, and we can also output a depth map, but it's not like a method for depth. I don't know if I understood the question.
Yeah, I kind of meant that nerve actually represents the scene, like from the views, it reconstructs the geometry. But with these methods, you don't need to do that because you only output a new image, right? So you don't
Yeah, but also, I mean, first we didn't use the classical nerve that optimizes for the entire scene, but um, what they do, the nerve kind of optimizes to learn the scene itself, and this is how they produce the novel view. But they don't learn the 3D specifically. They don't output the 3D, and we also don't use the 3D. It's explicit in the
Okay.
you can, from the density calculation, you can output the depth, but it's not like the most accurate method for depth.
Okay. Okay.
Okay. Anna, do you want to? I think there are hands, and also
Yeah,
will you
Pablo.
manage it?
Let's go with Pablo's question. You can go
Okay.
ahead and ask. Yeah.
Yeah. Sorry. So if I understood, you're using nerve to do the denoising and using also the neural network. But if you're trying to apply this on the water, is not needed to consider also the fact that the deep of underwater, because maybe I misunderstood it. Sorry, but there is going to be less visibility on further points on the image. So have you considered that?
Yeah, I mean, yeah, this is, I mean, for a topic for now, like ongoing work. But the thing is, you're right that there is the model, like the graphical model of nerve, it doesn't take into account the water. But it's not that it fails completely, because if you take the views from more or less same distances of the scene, then it's I mean, it's better to insert the effects of the water on the light uh, on the scenes, but it's not so. I mean, it's not that it fails. It works kind of maybe less well, but it still produces some results. So the water influence the model, but they don't break it completely. If,
Mm-hmm. I was just in case that maybe try to apply this water contribution using the distance may help to improve the results. I don't know. Just
no, for
I was
sure you're
thinking
no,
aloud.
you are right. For sure you're right, and we will try to do it. Just if you more or less took these views, let's say you tried to take a burst, but you moved, and but you didn't go very, the distance from the object didn't change so much. So then there is an effect of the water, but the effect is the same on in all the images.
Okay.
So it for sure it will improve, but also now it's, it kind of works.
Okay. Thank you.
And
Yeah, and if you want to go back to the chat, there was another follow-up question from Juan.
yeah, I think it was also the reproduction of, so it's related to the question of
Yeah.
Pablo. It's a good question. I'm happy with these questions. It means you understood at least what I was trying to. You're right that nerves do not handle underwater now, and this is I mean, it's an interesting direction to look at to model the underwater issues with yeah, with nerves.
Okay. So do we have any last question maybe? Because I think Tali, you need to leave sharp, right?
Yeah. Join another.
So yeah. So I think this was just in time. Then we can leave you 1 minute to switch to the other meeting.
So
And
thanks a lot. So for the attendance and the questions, we have everything on our website. So if you want,
thanks a lot to you, Tali, for accepting again. And yeah, hope to see you soon.
in
And
person.
yeah, in person, definitely.
Bye.
Okay, thank you, everyone.
Bye.
Bye bye. Thanks.